Thank you for taking the time to catch up and watch this video and maybe do a little bit of work on our differential equations so we can be caught up when you return on Friday, most likely Friday, February 27th for class. When you return to class on Friday, we will have our quiz on 6.1 through 6.3 through differential equation models. So right now, I want you to take some notes on these differential equation models. And if we go ahead and look at a couple of these models, then we'll be caught up for next week when we're going to stay on track and take our test on Chapter 6. So what we discussed on Monday for the beginning of Section 6.3 is we looked at a differential equation. And we talked about what the solution has to look like and what the graph looks like. So this is where we are so far. We know that if we have something in the form of, we have a differential equation, dy equals k times y, we know that's going to give us the solution that looks like y equals c e to the kt. And this is going to represent growth. That is going to be a growth model, and we know it's going to look something like this. We know that if we had a differential equation in another form and we have y equals c e to the negative kt, that's going to be decay. But we didn't really talk about a differential equation to match with this solution. What we did talk about was if we had a differential equation in the form of dy equals k, a big Y, minus a beginning value. And this becomes the differential equation y equals beginning minus ce to the negative kt. Or I'm sorry, there should be a plus there. All right. This was for Newton's law of cooling. And we know, because it's Newton's law of cooling, here's our beginning value, our surrounding temperature or beginning temperature, current temp. Whatever the number is in this part of the differential equation is going to be the number that's at this spot when you write the solution. So if you recognize a differential equation, you already know how to set up the solution to the differential equation. All right. So we know that this type of graph is going to have a starting value, but it's going to decline to an asymptote. So this usually is room temperature or whatever temperature is the surrounding medium where they need it to fall to, whatever it's going to cool to. So it's going to decline. All right. The next model we talked about was another form of growth, but with a limiting value. And its differential equation looks like dy equals k, and the number that's at the beginning of the parentheses is the limit of the growth. It's your limiting value, minus y. So there's your differential equation form, and you know when we can anti-differentiate, we do a separation of variables, but your solution is going to come to y equals limited growth, limited value, minus ce to the negative kt. So the graph is going to look like this. This is where it's going to top out. There's that limit. And the graph's going to start with a beginning value and climb toward that limiting value. And this was the problem we talked about in class, where we had the population, the rate of change of coyotes, the population direct proportional to 650 minus NT. That fit into the limiting values at this place. That 650 turned out also to be the asymptote for the solution of our graph. So whatever number's here in your differential equation is also the limited number for your growth, which will be your asymptote for your graph. All of these are related. The differential equation, the solution, and the graph, they all have pieces that fit together that tell you something about the solution. All right, so you had one for our homework. I'm going to put that in another video. So my video 2 and what I post today is going to be from page 429, number 59. So I'm going to post a separate video on that question. All right, so continue with our notes about differential equations. There's one other form that we started talking about, but we didn't really get to discuss. It was toward the end of class. So if you have a differential equation in this form, dy over dt equals ky, and a 1 is the beginning of your parentheses. So the first thing in your parentheses is a 1 minus y over, and this is going to be a value, but it's got to be in this form. It has to have a 1 there, and this has to be a y over another, then it's going to be a number there. That is going to be your limiting value. So what's different here is you got your rate of growth or decay times y. This has never been a y in that spot. Parentheses 1 minus y over L, and that number is important. Now we can do our separation of variables, and we can do our differentiation, but this one most times allows you to jump right to the solution. The solution, this is your differential equation. Your solution is written as y equals L over 1 plus b e to the negative kt. You know if you have a differential equation in that form, it will end up being this solution. So when you do the homework problems on this particular set, part of your job is to recognize, is it in the correct form? If it's in the correct form, this value is the numerator. Then you can plug in 0 for t and the beginning value, initial value where they give you, and solve for b, and then set up your equation. So going from this form to this form is important according to what you recognize. All right, so at this time, will you turn in your book to page page 428. We're going to look at example 10, and I'm going to work that with you. So if you have your book at home, page 428, example 10. If you don't, then we can just work it as you watch me put down the information. All right, so it gives you a differential equation. I won't read it to you. I'll just go ahead and put down the differential equation. And this is talking about a population of elk. And it started with 40 and talked about the growth after a certain amount of time. But that's okay. I recognize this form is in this particular differential equation form. Therefore, I know what the solution looks like. The solution will be P equals L. L is the denominator because there's a 1 right there. I'm in good shape. So this is 4,000 over 1 plus b e to the negative kt. I know that much information. All right, so I know the initial population, so my initial value, the initial amount introduced into the refuge was at time 0, they introduced 40 elk. All right, and then after 5 years, there were 104. in the particular environment where they were observing this population. All right, so we know that this is our initial value, so let's plug in 40 for the population. And at time 0, but ending the 0 power is 1. So nicely all of that becomes 1. I got 40 equals 4,000 over 1 plus b. Using our algebra, 40 times 1 plus b equals 4,000. So 1 plus b is equal to 100, and b is equal to 99. Therefore, the form of this equation is going to be p equals 4,000 over 1 plus 99 e to the negative kt. This type of differential equation and this type of solution has a name. It's called logistic growth. And all logistic growth has rapid initial growth, then it levels off to its limiting value. In this case, this limiting value is always the numerator. So I know it's going to top out, get close to 4,000, most likely not reach it. I know where it starts. It starts with 40. So I'm going to grow quickly and then start to level off. So we just don't count this as negative time, but I know my graph has that shape. This is logistic growth, and it matches with this type of differential equation and this solution. All right, so next we've got to find the value of k. All right, so again, here's my solution. P equals 4,000 over 1 plus 99 e to the negative kt. That stands for population. Sorry, it's so messy. And I know after 5 years, I have 104 elk. So 104 equals 4,000 over 1 plus 99 e to the negative 5k. Use your algebra again. And we're going to just drop down into divide both sides by 104, subtract 1, divide by 99. You're eventually going to get e to the negative 5k equals 0.378 through your algebra, and you're going to find the value of k is going to be 0.94 after you take the natural log of both sides and then divide by negative 5. So the solution is going to be p equals 4,000 over 1 plus 99 e to the negative 0.194 t. All right. Use a model to estimate the elk population for 15 years. So you're just going to plug in 15 for the value of t and use this on your calculator, and you're going to find that it's approximately 626. This is just calculator work, and you can use your calculator to find that value. All right, I'm going to stop here with the notes. I'm going to post 2 more videos. One video is, like I mentioned earlier, page 429, number 59, and also I'm going to work the homework to go with logistic growth and post a video. That one will be a little bit longer because I'll explain the homework as I work it. So look for 2 more videos posted on the course page.